Hi, I'm Ken Boydston. We're here in Vienna in a small room upstairs at the Austrian National Library, and we are imaging some manuscripts of various kinds and demonstrating some of the capabilities of the MegaVision multispectral system. So what we have here is a complete system in a very small room, but you can see that it's got all the necessary elements for taking pictures. We have two lights with diffusers. Each of the lights that we have has 7 visible bands. They have 5 infrared bands and an ultraviolet band. So we can shine different colors of light on the manuscripts, and then by doing that we can break the color up into very narrow spectral bands and see very accurately what the color of the manuscript is that our eyes can see, and in addition to that we can see things that our eyes cannot see. What we have is a camera with a lens and a digital back and a filter wheel and a laser alignment bar and some precise ability to move the camera in small increments to accommodate changes in the thickness of a manuscript or in small differences between the focal plane and the scene plane. Over on the shelf over here we have the computer which is controlling the entire process. The operator, which today is mostly me, will set the computer to a particular set of operating parameters, and then when the manuscript is set and we're ready to shoot, the computer will then take control and shoot an entire sequence. Today we've been shooting and will continue to shoot a sequence of about 31 pictures. Why 31 when there's only fewer than 31 different colors is that we will, in addition to shooting with both lights on at the same time, we'll turn one light off and shoot with one light on to give raking light, to give a little sense of texture, and then we'll also put different filters in front of the lens while we use the same color light. So we'll see what different filters result in different bands of fluorescence. So that's kind of it in a nutshell. Let's get started. This lens is a custom lens that we had to design and make for this application. A normal lens will be apochromatic over the visible range, but we need the apochromatic over the UV way into the infrared. So whereas a normal lens is going to be apochromatic over maybe 450 nanometers out to 700 nanometers at the most, this lens is going to be apochromatic from 350 out to 1100 nanometers. When optics bend the light, different colors of light are bent different amounts. And the modern lens design corrects for those differences and makes a compromise for everything. So there's a large rear element here as well as the front element, and in order to keep this thing in sharp focus over the entire range of wavelengths, it's got a floating element in the front to adjust for different working distances. So we focus it a little differently than you'd normally focus a lens, where you're changing the lens elements relative to one another. A Copo lens like this changes, and normally you would focus it by moving the lens up and down. In our case, we leave the lens fixed and we move the back up and down. So this is a filter wheel. So the purpose of the filter wheel is that if we're looking for fluorescence where the object is fluorescing, then we will excite with a short wavelength light like blue or ultraviolet, and then use the filter wheel to filter out all that color light and only let the fluorescing light pass through. So that will often let us see things that you cannot see otherwise. And that's the gigabit Ethernet for the camera data, and then a USB. There's actually 2 filter wheels in here. And so each filter wheel has its own USB cable. We will not image the entire folio with one picture, because if we did, the 50 megapixel camera wouldn't produce a high enough resolution to satisfy our demands. Each of the folios will be around 14,000 pixels by about 6 times 2 is 12, about 10,000. So about 14,000 by 10,000 pixels. It will be a larger picture than any sensor that's on the market today can capture. You can take a look at that chip. It's a large image sensor. It's a monochrome sensor. There's no color. This is 36 by 48. The problem really is the lens. The optical resolution of a lens, of a general purpose lens, will limit you. So the MTF of the lens isn't going to support that many pixels all at once. The lens will start limiting the resolution even if you had the pixels. So by stitching it, we're able to solve the lens problem as well as the lack of pixel problem and get the kind of resolution we'd like with today's technology. If these images are going to be looked at in 100 years or 200 years from now, to get some historical perspective on what the object looked like today, then if the color reference is there in every picture, then it really makes it easy to do a comparison. We always make two versions of the file. We make a raw file, a DNG, and then we make a TIFF file. And the TIFF file, the difference between the TIFF file and the raw file by default is that the TIFF file has been corrected for any non-uniformities in the distribution of light, so it represents a distribution of spectral reflectances in the object. And then from that TIFF file, we would create other files that are of interest, like a JPEG file, maybe a low-res JPEG or a high-res JPEG, and also from the collection of TIFF files, one at each of the spectral bands, we create a color picture from that. And then from the color picture, our default of the color picture, because this is not an RGB camera, we have a lot more color information that's available. So our default file format is a LAB file. So we make LAB as the default color space of the camera. We call it an LAB camera because it takes CIE LAB color. So it's more like a scanning or an imaging spectrophotometer. The compensator, you set it for the working distance from the focal plane to the scene plane, and then you focus the camera after you set the compensator. So you need to, before you focus, you need to roughly know your working distance. If you don't set the compensator, then the focal distance will change slightly with changes in wavelength. We're just testing the exposures of the individual visible lights on each side, on each panel. So we'll step down through all the different colors. There's 7 different visible colors. Each time we change, we take a shot and we monitor the exposures to see if they're about right. And it looks like they're looking pretty good. So the first thing I'm going to do is set up the metadata. Greek papyrus. Let's shoot some pictures. Let's see if I did everything right. The UV is nothing because the UV has a hard time going through the glass. The glass would be UV coated, so it's going to be really terrible to try to... The colors will look okay, color pictures. but the and the infrareds are dark too. Not sure why. This is where it's nice to have a chair. I might bring in a chair when we start doing the... Not that we need one more piece of furniture in this room. Now we can take a look. So you see the parchment is, I mean not the parchment, the papyrus is actually fluorescing quite a bit. It doesn't fluoresce much under blue. But the UV, it's fluorescing really quite a lot. I think that should be it. So these are the raw files here. Let's sample this here where it's not too grungy. And we'll do a white balance, and we're going to use 1, 2, 3, 4, 5, 6, 7. So I'm going to do a white balance using the first 7, which are all the visible wavelengths. Alright, so here it is. And there's the color picture. Here's what we've got. This is a little bit interesting. The text, where the text is very hard to read, when you have the parchment there, there's a lot of clutter in the background. But under the infrared, the clutter in the background disappears, leaving only the ink. So it'll be a little easier to read looking at these infrared files. This is a laser alignment tool, and it projects 2 lines onto the scene. Those lines, when the scene plane is parallel to the focal plane and the scene plane is the correct distance for focus, then those 2 lines merge into one line. These lines now merge at this distance, and we're ready to shoot. One, 6, 8, 6, 7. Okay. Whoa, that's spectacular. Okay, so this is damaged, unreadable up here. This is damaged, virtually unreadable. A little few text right in the middle. Okay, so that's pretty good. It looks pretty sharp. I think we didn't make any too big of mistakes. I think everything looks pretty good. You can't really make out any of that text there in the color image. So that's how it's going to look to you on the page. I think we could read this text. I think they'll be able to read this text here. So that'll be helpful. So this thing fluoresces, but the fluorescence is not discriminating any text. Oh, but down here it is. Aha. Okay. So down here, the UV reflected light is obscuring everything, but the fluorescence does reveal. So with a little processing, we could probably get this text down here. So if you look here, in this text up here, this text is pretty much lost in the visible. And in this one, nothing. But in this one, you get most of this text up in here. I think with a little work, maybe a little principal components, that text is going to be very legible. Down at this end, not so much, really. Nothing in this one. This was productive up there. In this one, okay, we've got some contrast.
Yeah.
We certainly have produced some possibilities for reading that. This will take a little bit of work down at the bottom. Maybe combine a couple channels, principal components. But I think it's interesting that down here, this channel here, this is just looking straight at the one of the filtered channels. It's nothing, and yet that same one up here is really quite productive. So you just don't know what is going to work exactly where.